It's exciting class today. We're going to do sums of squares optimization, which is one of my favorites. The big goal for today is to address what I consider to be the only real major limitation, but it is a major limitation to what we talked about in the last couple lectures. Basically, the last few lectures, and including the very last lecture, we gave cool algorithms that started off by saying, pick a bunch of sample points, xi, and then you can write an optimization to, for instance, find a Lyapunov function that, if I were to parameterize it as a linear combination of nonlinear basis functions, I could write down the conditions that v of xi is greater than equal to 0, let's say, for all xi not equal to 0. V of 0 equals 0. And I could say v dot of xi less than or equal to 0 for all xi not equal to 0. V dot 0 equals 0. And I could say, I can write an optimization to say find alpha subject to those conditions. And because this condition is linear in the decision variables alpha, and the derivative, it turns out, is still, even though this one works out to be now alpha v dot looks like alpha transpose d phi dx f of x, right? The derivative is also linear in the decision parameters. So this optimization is a convex optimization. And so far it's a linear program. In fact, in that example, I pushed I played with the numerics of it, the one about the pendulum recovering the mechanical energy. I played around with some of the different implementations. The numerics work really well if you add something else to sort of. So the problem if I just have only these equations on the board is that alpha being very, very small, so the v is very, very flat, is just as good as alpha being very, very big, and there's sort of no reason for it to pick something that's, extremely shallow or extremely tall, right? There's so many v's that can satisfy these equations that I haven't given it any preference to picking one that's not, numerically bad. Something that's very, very close to 0 down to a decimal place can satisfy these equations, and solvers don't like that. So I put in an additional objective to make the numerics good, which said minimize the difference between v of x and -1. So I said, basically think of it as the cost to go being like going downhill for the minimum time problem. So I said v of x plus 1, which is equivalent to v of x. I want it to be around -1. So I added this as an objective. And then there's a question of, do you add it in the L2 norm or in the L1 norm? Do I minimize the squared value of this? That would give me a quadratic program. I found it numerically better to minimize the absolute value of that, which is a linear program. The solvers just performed better against that. So I optimized the absolute value of this, which is a linear program, and I hope you'll look at the code and see. Now that's partly a function of, was that clear? Yeah? It's partly a function of the fact that the open source solvers we can distribute with the class aren't as numerically strong as the commercial solvers that we normally use in our research. So, it shouldn't matter. Like either of them should be trivial problems to solve. It just happens. I mean, I think this one really is numerically better, but so I went with that. Okay, so this is awesome, right? So we have a convex optimization that can find the parameters of a Lyapunov function alpha. And in the cool case of the pendulum, damped pendulum, it basically recovers mechanical energy. I gave it a lot of different basis functions to choose from. All the ones that didn't appear in mechanical energy came back with coefficients numerically equivalent to 0. They were like 1e to the -7 or smaller. And then the terms that you'd expect to see, one of them looked like a scaling of energy, right? A constant factor away from energy. Super satisfying. The only thing I don't like about it is this. And right at the beginning of, back in dynamic programming, someone asked, how do you choose the sample points xi, right? And for a two-dimensional system, it's not hard. You just dump a bunch of sample points, and as long as they're sort of dense enough based on how fast your functions change, it's not hard to pick those in 2 dimensions. When you start trying to scale to higher dimensions, this becomes a bottleneck. You don't know where to put the sample. You can't choose as many as you'd like to cover the space densely, because the number of points you'd want to even get a uniform grid over a higher dimensional space, it grows exponentially in the size of the space. And it's hard to know where you need to sample. Now, it's not to say there can't be really nice work, and there is not really nice work out there about how do you selectively choose those points. But I really want to do better than that. I don't like that if I increase, the number of constraints I have to add in my problem grows exponentially with the number within my dimension, because I have to add a new one for every sample point. So is there any hope of doing better? And the other thing is, it's not an official proof, right? So I've only actually verified this condition is true at those points. So there's really nothing to say that there could be something happening in between those points that violated my Lyapunov conditions, and I don't actually know. It's not a mathematical certificate yet. So the goal for today is to go from this to saying something I'd like to say for all x. I'd like to replace the statements that say for all xi, I'd like to say for all x, and no sample points required. Okay? Turns out it's possible in a number of places. The simplest one to understand, and the building block that we'll use, starts with linear systems. Okay, so if someone gives you a linear system in state space form and asks, is it stable? If you can construct a Lyapunov function and certify it for all x, then you'll have answered the question, right? You could also check the eigenvalues, but we're going to ignore it. That's not the cool way to do it today, right? Okay, so let's try to do it with the Lyapunov function, right? We're going to write v of x is some quadratic form. This came up in this was the choice for the cost to go also, and it's going to be a good choice, the natural choice for this. I didn't really say before why this was a good choice, but someone asked me after, and I wished I had said it. So why do these things tend out to be quadratic for linear systems, right? So imagine, in the cost to go case, imagine I had something like, I want to evaluate something like this for some positive q. Well, the solution x of t, this is at t, right? The solution x of t for a linear system looks like e to the at x0, right? So if I want to understand the integral of this, I could write this as x0 t e to the at q e to the at x0. And that x0 in terms of this integral is a constant. I could pull that outside. So what I end up getting is something that looks like this. It's a nasty thing on the inside, for instance, but there is a reason why these things turned out to have quadratic forms. Okay. That's just sugar. This is, if you're willing to just go with me that the quadratic form is good, then let's pick this form. Okay, so what does V dot look like? So it's going to look like X transpose A transpose P of X plus X transpose P A of X. Which conveniently still looks like a quadratic form. So how can I, for all x, check that this v is positive? If I want to satisfy that for all x, exactly. It's exactly equivalent to P being positive definite, which is just, I'll try to remember to use the little bit more squiggly version of the inequality for the matrix inequalities, okay, as opposed to a scalar. This is a scalar. If it's more curly, that's my positive definite. Okay. The cool thing is, I can also check this condition for all x, right? My condition for all x not equal to 0, v dot of x is less than 0. By checking this thing, right? I just need that thing to be less strictly negative definite in this case. So these conditions here, now if I go to this version, these conditions have nothing to do with x. If I can check these coefficients, if I can satisfy those, I've got a certificate that it's true for all x. Right? I got rid of my sample points.
Why is v of x greater than 0 as long as it's positive definite?
That is sort of the definition of positive definite. Positive definite means that for all x, anything you multiply this x transpose p of x is greater than 0. That's the definition of positive definite.
Wouldn't that mean that ATP plus PA or ATP or PA is positive definite? Because what if, like, A doesn't necessarily have to be positive definite?
True. What you said, what was the implication you asked about?
Oh, that B, this would be, oh yeah, no, that is true. Oh, you're right, sorry.
No worries. Okay. So then the game becomes, how do I search for P's that satisfy this constraint? Right? What does that constraint look like? I mean, so think about how do you check for positive definiteness of a matrix, right? So, the minimum eigenvalue of P had better be greater than 0. That's not something I want to give my optimizer. That's kind of gross. But there's a magic, so this is no longer, that's certainly not linear. This is no longer a linear program. But there's a magic thing that, oh yeah, do you know? Yeah.
I check the pivots when you're doing row reduction. That they're all positive.
That works in the low dimensional case, I think, but it won't work in general. Yeah. That's the right kind of thinking. It's actually hard to squeeze it into linear programming, but here's a critical observation. Which is somewhere over here, but the set of positive definite matrices is a convex set. Okay? So, two-line proof, right? So let's say that A1 is greater than or equal to 0, and A2 is greater than or equal to 0, which means for all x, x transpose A1 of x is greater than 0, and then x transpose A2 of x greater than or equal to 0. So the thing you have to check is what happens if I have a new A, which is a linear combination, or an affine combination. So B times A1 plus 1 minus beta A2, where if A1 is A2, right? So there's some set of matrices, A1, A2. I need to say that if I picked any, this is the some set of positive definite matrices. My condition is that if I pick any 2 points that are positive definite, then the line between them had better also include the positive definite matrices. And I think you could see that if I stick this in, then the question is, do I have it? Is it true that for all x, A is greater than or equal to 0? And it is, because I can just stick it in here. This thing tells me that beta, which is greater than 0, x transpose A1 of x is greater than 0, plus 1 minus beta, x transpose A2 of x is greater than 0, and I can just pull the x's out, stick the betas in, shuffle, and I get this. Okay? So it's cool. So in the original in the matrix coefficients, if I have 2 positive definite matrices, then affine combinations of those positive definite matrices are also positive definite. Cool? So that means, although the algorithm might look different than LP, the way that people solve LPs is a little different, it's still a convex optimization. You still, if I want to write down a constraint which looks like this, then I should be able to solve that with convex optimization. There are other things besides the set being convex that make it useful. You have to be able to write a solver that knows how to start inside it and move around in it and things like this. But in practice, constraints like this are the stuff of convex optimization, and it's called semi-definite optimization. So we went from linear programming before, now we've gone to semi-definite programming. SDP. When you're on the notepad, or like when you're doing your theory, then arriving at an SDP is just as good as arriving at an LP. Like, they are both problems that you should expect to hand to a solver and solve to global optimality if you can write those constraints. In practice, the commercial grade linear programming solvers are way better than the commercial grade. There aren't commercial grade. I mean, there's barely commercial grade SDP solvers. All those details that I sort of just said, yeah, you have to be able to sample from the set, blah, 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 and the numerics and stuff, people haven't refined semi-definite programming to the same extent. but as long as you're gentle with them, if you add these constraints, then you should be able to ask a semi-definite programming solver to do it. Now, what do I mean? So if you ask for constraints where like the eigenvalues are almost 0, or like a lot of the elements should really be, somehow it's numerically, away, like if the solution, the only solution that satisfies your equations has like a 0.1 in the first column and then a 10 million in the second column, then that's a very hard thing for the solver to deal with. The linear programming solvers, when you do that, they're like, oh, silly, you could have rewritten this way better, and they know how to rescale the problem into a numerically well-posed problem, and then they solve the right problem that you should have written, right? SDP solvers don't understand that. They're not as good as that. They don't have all the pre-processing algorithms that get rid of the crap that you do. So in practice, if you're thinking about an SDP and you write it down, and you understand a little bit about SDP, you can write down things that solve really well. Oftentimes, when you have something that load from a URDF, load from a generic robot description format, ask a generic question and try to kick out a semi-definite program, then you ask the solver to do stupid things and it yells at you. And the way it yells at you, it says numerically infeasible or something like this, or so it's not quite as much of a hammer, but it's pretty darn good. That was a rant. Sorry about that. Okay, so while I admit you could have checked the eigenvalues, now you have yet another opportunity. You can use one of these solvers that I just promoted so well, and I could ask the solver. I could formulate a semi-definite program which says, find me a p. Semi-definite programming. So the generic form of semi-definite programming is find me some, is, let me write the generic form. So the generic form is minimize over some decision variables p. You'd like them to be in the symmetric matrices. So you want it to have, this is the symmetric matrices of size n. Okay, so you're looking for matrix P that satisfies some conditions. You have a cost function that's typically written something like this. I've written X for all my other ones. Let me, before I get too far, change that to X. So that's a linear cost function in the parameters of my matrix X that I'm searching over. This is almost always written as the dot product between matrices C and X, okay? But it's like the LP, it's just linear objective in the coefficients. And I can now add my traditional LP, any linear constraints, but I can also add the condition X is greater than 0. It's positive, it's semi-definite, so numerically it's only going to do that for you, the positive semi-definite. Even more interesting is you can add any sort of constraints of the form AKX is, let's say, less than or equal to BK, to keep it in the same form. This is linear, these are called linear matrix inequalities. LMIs. So anything like this, for instance, which is linear in the coefficients of the parameter matrix P, okay, but it's a new matrix, and I'd like this new matrix, which is a linear function of my original decision variables. If I want to constrain that linear thing to be positive semi-definite, then you're allowed to do that. Yeah?
So is P a vector or a matrix?
This is actually a scalar. So this is the sum over ij of all elements. Yeah, that's a good question. Okay, so now we could ask this exact question by say, find me a p subject to this condition and this condition, and that's a semi-definite program. Okay, so you wanted to take the eigenvalues, that's fair. But this now opens up the door to much more interesting, this is a more general purpose solution to that same set of equations. Yeah?
You say x has to be symmetric there?
Yeah.
And then one of your, but none of the matrices here are symmetric.
P is symmetric. I'm going to search over symmetric matrices P.
Would we state that P has to be symmetric?
I should have written here to make it a good positive definite quadratic form. Yeah, that's my choice. Is I'm going to search over the And it was the same way in LQR. We chose Q and R to be positive definite symmetric. Thank you for catching me on that. Okay, so let's put one of the more advanced tools to work now that we have more general machinery. So what if I have x dot equals a of x, but I have uncertainty here? So now the question is, x dot of a equals a of x, is it stable? Yeah. And, by the way, I don't know exactly what a is, right? So you have to somehow answer the question, can I prove it's stable despite the uncertainty bounds? Cool question? Yeah? Let me say that one more time, just in case. So let's say you have a linear system, you know it's linear, but you don't know the parameters of your matrix A. Okay? Can you find a commonly Lyapunov function, guess what, using semi-definite programming, that can verify that this thing is stable even though you don't know the parameters of A? That's something you can't do with eigenvalues. Okay? So you actually need the SDP form. So first question is, how are we going to write that A is the uncertainty on the elements of A? I mean, think about it. So if you're doing it and you're writing down A, what would you do? You'd say, I don't know, the third coefficient, it's probably 2 plus or minus, 0.1, something like that. You'd like to put some sort of uncertainty bounds on the elements of A. What's a nice general way to think about that? Let's say that A is a convex combination of other matrices AI, okay, where AI is greater than or equal to 0, sum of B to equals 1. That makes it a convex combination. So in the coefficient space now, I really have that picture I started to sort of want to draw before. A1, A2, A3, A4, A5. So if you took any element of my matrix, and I'd say it's between, I can look at whatever that dimension. It's got to be inside the set defined by those extreme points. So in the simple case, I could have just A1 and A2. Funny that I went like that, huh? But I could just have A1 and A2, and they're all identical except for the third element, which I knew had some uncertainty. A1 has 2.1, the other one has 1.9. Okay, and then this would work. All right, so I'll say that A is some affine combination of this, and that allows anything inside this convex region to be A. In the coefficients. Does that make sense? Yeah. Okay. So we can write the conditions that say, if I want to say find me a P subject to X trans, that P is greater than or equal to 0, and for all I, AI transpose P plus P AI is less than or equal to 0. That says that the P I find, if I can find a P that satisfies that, the P I find works for this system, works for this system, works for this system, works for this system, works for this system. That's all it says so far. Until you observe the fact that if you have that true here, then you can actually certify that it's true for all A inside. Easy to see. So what is the, what's V dot for A? Is, there's an X. In this form, there's an X. Okay, so since B is positive, right? If I can break that apart, since every one of those individually is positive, is less than 0, then this whole thing is going to be less than 0. So in the particular case of this example of bounding linear matrices like this, then it turns out that proving stability for all of the vertices is sufficient to prove stability for any system that is inside that convex set. Okay, and this is a semi-definite program. That's cool, right? We know about the tightness question. Even if there are systems, there are certainly there are systems that are stable, that are guaranteed to be stable, that it's too much to ask for a single Lyapunov function to prove stability of all the bounds. But if you can find a P that satisfies those equations, then you have certified for all X that this thing is stable. Now, it's not very graphical, but I did work hard again on it, so I'm going to show you. And maybe what's cool about it is how simple the code is. Is that cool? Okay, so first I generate a handful of random stable matrices. So you can do that. There's a handful of ways to do that. The simplest way is to do that roughly. You pick negative eigenvalues and then any unit matrices, and then you multiply them together. Okay, so that just generates a handful of stable AIs. And then the else case is something I actually decided not to include. But okay, so here's the whole program. I start a new mathematical program. I say, make me a new symmetric continuous variable, P, the matrix of decision variables, P. Okay. Add the semi-definite constraint that P is greater than 0, roughly. But look, if you notice what I did here, why did I do that? Why did I do this 0.01 NP identity? Sorry if NumPy isn't super readable, but why did I throw that extra little term in there? SDP is only going to tell me whether P is greater than or equal to 0. I'd like to ask a stronger question. I'd like to certify this. How do you do that if your tool only certifies this? Right? I said, I want this to be greater than something small times I. okay? And then, which is equivalent to checking this. So that's a trick to get actual positive definiteness out of a solver that only knows how to do positive semi-definiteness, okay? And then here's my common Lyapunov function for all of the AIs. That's my condition, and I threw in a little, make sure you're really negative definite in there, the 0.1 again, 0.01. I put an objective in. You don't have to, but I'm in the habit of doing it because, again, you don't want to leave the optimizer too many options. It's better to sort of tell it what you want. So this is just saying, give me a small, reduce the trace of p, so somehow makes p smaller, all things equal. Okay, and then I just print out some stuff. And because there's no guarantee it's going to work, I have to check. The solver will either say, yes, I found a solution, and then I have a guarantee, or, sorry, it just didn't work, you know. But that means that there is no p which satisfies those conditions. The solver is doing its job, but it might be that there is no p for the random stable matrices I picked, which certifies all of them simultaneously. We know that for any one stable matrix, there exists a p, but there might not be one that satisfies all of them simultaneously. Okay, so there we go. So it found a p, I just took the eigenvalues to convince you. P is actually greater than 0, but just barely. See, if I hadn't put that 0.01 in there, it would have driven that right to 0. This is, by the way, you know, starting with random matrices, right? So I don't know what's going to happen, right? But those numbers are small enough that it makes me think if I hadn't put that in, that would have driven that to 0, and I wouldn't have I would have had p semi-definite. And then this is my p dot is my shorthand for the negative definite condition, and they're all negative definite. But the interesting thing is it doesn't work every time. So there you go. See. It works a lot of the time. And of course, I'm asking. This is harder than what you'd have in practice, right? So I'm just saying, pick 3 random matrices that are all stable, right? It's not like I've got a robot and I'm uncertain with mass between 0.1 and 0.2. I'm asking a much weirder question. I'm saying, here's a stable matrix. Here's a stable matrix. You know, can you certify all of those, right? So your experience hopefully is better than 1 and 3 with that. So something really big happened here. We proved something for all x for a non-trivial system at this point. It's a linear system, but it's uncertain. So the big question then is, can we do the same thing for nonlinear systems? Is there any hope? Right? This was leveraging positive definite matrices as a way to say something about all x. Can we say anything like that for nonlinear systems? Here's the key idea, and it's super simple and intuitive. You're not going to think that at the end of the lecture, but just think with me for like 3 minutes, okay? Super clear and intuitive way to generalize that result. So I was saying V of x is x transpose P of x. What if I were to just to generalize this to richer V's, because I'm going to have to deal with richer dynamics? What if I now try to do V of x is some basis functions, I'll call them m here, times, let me change the notation because I'm going to get too many p's on the board in a second here. Q is just as good. Q m of x. This is some sort of any constant. There's no parameters. There's no decision variables inside there. Potentially nonlinear vector function, right, of x. It's like my phi of x before, but I'm now writing a quadratic form here. What can I say about that? Well, if q is positive, so the definition is of q being positive is that anything you put here, anything you put there, is going to end up with something greater than equal to 0. So that even if I can hide it behind an m, but that's not going to change anything. So this should still be positive. Checking the coefficients of q to be a positive semi-definite matrix still certifies that this function is positive, even though I've opened up my class of functions. Yeah? Here's the rub. So that's the that is the generalization, that to that, okay? But we have to do a little bit more legwork to make it work for us, because if I think about now the more general dynamics, the problem is, there was a magic thing that happened here is that I took the derivative of this and it still had the same quadratic form. I'm going to take the derivative of this and it's not quite as nice, right? So v dot of x, it's not that it's scary, it's just that it's not the same form as v was. Okay? So v dot of x is going to be what? M transpose, let me write M transpose x q. I'll do this side first. Partial m, partial x, f of x, and then plus the other side of it. So my task, I can't now suddenly factor this whole thing. I don't have that same quadratic form. So it's this one that screws things up. I can certify this is positive definite by finding and searching over Q, but I don't have something I can pull out of the inside here that certifies it the same way. And in general, this could be a jumble of it's a scalar equation, but it doesn't necessarily have that same simple form. It might. It's actually possible that it does. It's just hidden inside here, right? If I had a bunch of sines and cosines or something in here, and I got some sines and cosines, I've got a derivative, is going to keep me in the sines and cosines or whatever. It's possible that I could rearrange this for any given m and f and find inside that a form that looked like that. And that's exactly what we're going to do. But we're not going to do it because that's hard. We're going to ask the optimizer to do it for us. Okay? So we're going to say, is this equivalent to some other m possibly? X, q bar, m of x? Right? If I can find, even though I've got a sloppy set of equations here, if I can somehow make it equivalent to something like this, and it could even be that m changed, it doesn't really matter, right? If I can write it like this, then I've got a proof. That's one view. Let me come at it from another slightly different angle now and tell you sort of a separate way to sort of present the same thing. Here's a question. Is 1 plus 2x squared greater than or equal to 0 for all real x? Yeah, right? That's positive. That's got to be positive, right? How about this one? For all real x. This one I don't expect you to do in your head, but I can prove it to you by rewriting it. I mean, it's actually the quadratic formula is not going to be the simplest way to see it. The simplest way to see it is if I rewrite it like this. Okay, you multiply it out, unless I made a typo or something, but these coefficients should match. And this is greater than 0, this is a square, so it's greater than 0, this is greater than 0. Okay? So if you see it in this form, then it becomes obvious. This is a sum of squares. Yeah? That is a sum of squares. They look a little different, but they're the same thing. That's just a quadratic form. I put m's in. Then searching over q becomes equivalent to searching over, it's finding the factorization of an equation into the sums of squares decomposition using optimization. I have to say a little bit more for you to believe me, I think, but it's awesome. So the way I'm going to do it, if I have something like this, I'll do this one's less writing. Then what I'm going to ask is there a quadratic form that proves that that is the sum of squares? That proves that that's positive. So I can pick any monomials. Let me pick 1x, x squared, which is actually a stupid choice. I only need 1 and x, but I'm going to do this just so you can, it's a slightly better illustration, I think. And I've got some quadratic form that I'm going to search over. Okay, so q11, now q21, q31. Remember, I'm going to search over the symmetric positive definite matrices. So even though my notation looks like it's wrong, I could write 1, 2 here and say it's equal. Yeah, let me see that. Those are the same parameter, right? So if I can find a positive definite matrix Q, which also satisfies the constraints that the coefficients that lined up to be 1 are, which on this side is just 1, and on this side, the only ones that can contribute to my constant terms is this one. So Q11 has to be 1, right? What's the only ones that can contribute to the x squared? Well, actually, I have a bunch of them, right? Because I have anything that touched that with 1. I think I wrote it down here. I said Q22 plus 2 Q31. That had better sum up to equal 2. Okay. Q33, that's going to give me an x to the 4th term, so that had better equal 0, right? So on and so forth. A lot of the other ones have to be 0. Here's the magic. Matching coefficients for this polynomial in this case and this matrix give me more linear constraints, right? Coefficient matching, if you will. So asking whether this is positive, if I specify this monomial vector, m of x, right? A polynomial, this is a polynomial, anything that just has one term, no sum terms, but just one multiplicative term is a monomial. So given this and given this, then I can formulate a semi-definite program to certify the positivity of this. Okay? That builds directly on semi-definite programming, but that gives me a new class of convex optimizations I can ask for called the sums of squares optimizations. So I can minimize over parameters alpha any linear objective of my alpha subject to some polynomial, let's say, in X. And the way we write it is sums of squares. This is almost the same as saying for all x, p of x alpha x greater than or equal to 0. Certainly, if I can prove that p of x is a sum of squares, then this is also true. This direction is not the same. It's not quite identical. There are functions that are positive everywhere that cannot be proven to be positive by sums of squares decomposition. But we're going to totally ignore those because that's like people name the polynomials that they found that are not sums of squares. Like the Motzkin polynomial is the most famous one. It's like, hey, I found a fourth order polynomial that is positive everywhere but is not sums of squares. It's like if you had to look that hard for it, then I'm happy to just act through. I think also when we're searching for the Lyapunov functions, we have enough freedom that this gap doesn't hurt us. So. Mind the gap. There is a gap. Sums of squares does not quite, the sums of squares polynomials are sort of a subset of the positive polynomials. But for all intents and purposes, I think it's close to, actually I know it's a strict subsetting. But for the purposes of today, it's as good as it's certainly a true certificate of optimality. And in practice, when we expect to be able to find one, we do find one. Okay. So I've got a new optimization I can write. I can say, so if I write down a polynomial, I could say, is this a sum of squares? And behind the scenes, the sum of squares, algorithm, solver, is just a front end on the semi-definite programming solver, which writes this. It says, make some new decision variables Q, add a bunch of constraints to make sure the coefficients of my polynomial match up with the coefficients of the quadratic form. Right? If this had been alpha 1, if that was a decision variable, that's okay, actually. It's still linear both in alpha and Q, which is amazing that you can search. So if this is a polynomial with coefficients alpha, so you can search over the coefficients of the polynomials inside the sums of squares polynomials. Remember, it's easy. It's just that, right? You guys look not quite happy, like happy but not quite happy. So can you ask questions that'll help? Yeah.
What's the relationship between the polynomial and the original linear coefficient factor? Like C triplets alpha and polynomial alpha.
So the polynomial of alpha, I'm saying that I have like alpha 1 x1 plus alpha 2 x2 plus alpha 3 x1 x2. Right, so I've got a polynomial, and it's just the coefficients of the polynomial. So I have a polynomial in x. It's the coefficients that are alpha. And because the polynomial is, the coefficients of a polynomial enter linearly, that's what allows me to do this coefficient matching linearly.
Where does the polynomial come from?
Good. So this is the same way that before I said for least squares function approximation for everything, we picked a basis function, phi. Now we're going to pick the basis functions, which are x1, x2, x1, x2, right? And then the coefficients. So this is exactly like alpha transpose phi of x that I wrote before, but now phi is a special form. It's a monomial. So I'm going to be thinking of this as alpha m of x. So every one of these is just some multiplication of the elements of x. Yeah?
The letter P, what does it refer to?
I put it in there for polynomial, which is why I changed Q up there, because I didn't want to have too many P's flying around on the board. And that's a lowercase p. Yeah. That's a good question. The other thing I did here, which nobody has called me on yet, is M works for any. I didn't have to assume polynomial up there. At some point I said, okay, let's do it. My example was a polynomial. And then I said sums of squares is about optimizing over polynomials. You can apply this to other types of functions. It works. Certainly that the decomposition works. The reason that polynomials is called out in sums of squares is there's some subtle reasons. So in the sums of squares solver, I can just hand you a polynomial like this. And there's reasonable algorithms for figuring out what given the right-hand side, you can figure out what the basis functions have to be, a sufficient set of basis functions. For instance, if I only have an x squared term here, I really didn't need the x squared term here. I just know that if I listed all elements up to degree divided by 2 in here, that I could have matched the coefficients. Even for multivariable polynomials, there are rubrics for writing out a set of basis functions which I know to be enough. And that's not true in sines and cosines and other functions. And also, sine squared plus cosine squared equals 1. So that, I don't know, that screws up something in here. You have to do all the bookkeeping for more complicated functions, but you can do it. The mathematics is much better understood. The tightness is better understood. The algorithms are a little cleaner if you restrict yourself to polynomials. So we often do.
So the polynomial is linear in f of x, right? It's also there's quadratic in f of x. That it's some quadratic, because
I hear your question. You could also write it as something that is quadratic in M, but don't do that. Because, so that would be a harder problem. So it is sufficient that if you can write it in M of x that's linear, choose that. They're both true in this particular example, but way easier if you have it linear, if everything's linear in your, having m squared doesn't matter, but you want to be linear in your parameters, alpha. And in fact, you do have m squared by saying, because you get m times a matrix times m, right? So if the whole thing ends up being m squared.
Why is
not for almost all x. I see that it's almost for all x. If you get this, if you find a p of x that satisfies this, that it is sums of squares, you have certified for all x, this thing is greater than 0, or is equal to 0 at the origin, for instance. What is not true is that if you fail to certify this, the system, it could still be positive. So I cannot write, I would like to say sums of squares optimization is minimize over this, subject to the constraint that this thing is greater than or equal to 0. I cannot in good faith write that because there is a gap.
Okay, so those would be polynomials in that gap.
There are named polynomials in that gap.
Yeah.
No, but so there's also theory saying as the degree goes to infinity, that set gets big and stuff like that. Like it's a real thing, but it doesn't bother me.
So for the linear case, we were doing an SCP to find the values of the P matrix.
Yes.
So in this case, are we plugging in the polynomial for V dot, partial and fx plus transpose, to prove that we can find the Q matrix?
Yes, exactly right. So there's a front end on the solver, which allows you to think just about the coefficients of your polynomial. You can write optimizations that say, look over the coefficients of my polynomial and just have a constraint saying it sums of squares. Behind the scenes, what it is doing is adding additional decision variables, Q, and adding a positive semi-definite constraint onto Q, and handing that to a semi-definite programming solver. It's tucking that away for you so you don't have to think about it when you call sums of squares. And the magic is that for polynomials, if I look at a polynomial like this, I know that, for instance, 1, x1, x2 is a sufficient set of bases functions for this, right? And you go to the maximum degree, there's something called the Newton polytope, which is sort of the simplest algorithm for chopping out the monomial basis that you really need, okay? There's also a better algorithm that Frank Permenter is working on, or has written up before, but he's porting it to PyDrake for us so that you get the best algorithm, hopefully this week. If you're watching, Frank, I just promised your algorithm. Okay. Good. So you're on the right track. So now, given this abstraction, we can ask the question for the Lyapunov question for a new class of systems. So let's consider x dot is some f of x, and let's say for a minute that this is a polynomial. And I say, here's v of x, which is some positive polynomial. There's a polynomial in the coefficients alpha. I can say, find me alpha such that v of x is sums of squares, negative v dot. Well, so the key thing is that this thing stays polynomial, right? So v dot of x, which is partial v partial x, f of x, that thing's still polynomial. Is sums of squares. That is now a question you can ask the solvers. And how does the gap get you? It's possible that there is a Lyapunov function, even a polynomial Lyapunov function, that proves that your system is stable, and you didn't find it. But again, it's very rare. Certainly if you do find one, which in practice we do, then it does certify optimality for all x. No samples required.
Right. In alpha, do you mean with coefficients alpha?
Yes. That's a better way to say it, thank you. With coefficients alpha. In fact, what I said is really the wrong way to say it. Thank you. Cool? So now here's the trick. This is like a new language. You've got a new type of question you can ask. And there's a million ways to take the Lyapunov conditions that you want to write and shape them into a question like this. And different ways that you do it will expose, will be sort of linear in different things. Let me give you a couple examples instead of waving my hands. For instance, the damped pendulum example, with a little bit of care to make sure that the sines and cosines don't cancel each other out the right way, I can pop that into sums of squares, and it also finds the mechanical energy and does it in a way that I now have faith that it's done it for all x. That just sort of works. But there are simple examples I'll do first. You have a question?
You said this, so that's supposed to be negative.
Thank you. Negative v dot is sums of squares. Good catch. So you can ask, the simplest question here is a question about global stability. The really cool thing is you can also use that tool to do regional stability. So remember the example that looks like this. So in the first order single variable system, I can just plot it. At the origin, this looks like negative x, and then this thing looks like x cubed, so it goes like this. Okay, and the crossings here are at 1, negative 1. So the region of attraction of this fixed point is that whole region. So here's the game. You've got an oracle now, roughly an oracle, that you can ask questions. Find me a function that is greater than or equal to 0 for all x. But I can only find a Lyapunov function I should only be able to find a Lyapunov function that certifies me in the region where it's actually convergent to the origin. So how do you ask a question of the oracle in a way that if it tells you the answer for all x, it has certified stability so just over some x? Right? What I'd like to say here is that, in fact, what I know here is that if I choose v of x equals x squared, then v dot of x, what is it? It's 2x negative x plus x cubed. That's right. So this thing is negative definite between negative 1 and 1. Right? This is less than 0 for all x in negative 1 and 1, apart from 0. And then it goes up. So remember we said we could do, if I have a set v of x, an invariant set v of x, over which I've certified my Lyapunov condition, then I can say something, I can say that's the region of attraction of my system. This Lyapunov function should be able to certify that. Can sums of squares do it for us? Right, so this is true that this inside that interval should maybe be a sums of squares. Afterwards, it goes negative. It goes positive, sorry. So v dot is negative when the x is small, and then this term comes up and wins after x crosses 1, and it becomes positive. Okay, so if you have a question, if you have the ability to ask, is p of x greater than 0 for all x, but you'd like to ask for all x inside some interval, let's say, how do you do it? There's a trick. It's like the trick from constrained optimization, the Lagrange multipliers tool from constrained optimization. Okay, so if I say p of x, let me say that this set is defined. If I want to say whenever g of x is less than or equal to 0, implies that. So if I have a different function that tells me when I want this to be satisfied and when I don't want it satisfied, then I can ask p of x plus lambda x g of x is sums of squares, lambda x is sums of squares. So let's think about that. So if I have a function that I want to make sure it's positive whenever g of x is less than or equal to 0, then if I prove it's positive even when g of x is trying to make me more negative, right? This thing is, when g of x is negative, this is trying to make it harder to prove positivity. I've constrained lambda to also be positive, so this isn't going to help. This whole term is just trying to fight my positivity. If I can still prove this despite that term fighting me, then I certainly have a certificate. Whenever inside this is this, that's true. Okay. Now the other the magic is that p of x no longer has to be positive outside the region. Because outside the region, suddenly g of x is positive, and even if p of x is negative, this is able to lift me up so that the whole thing is positive. Okay? There's lots of ways to look at it, but just algebraically, this thing helps you when you're outside the region. It's making it easier to certify sums of squares in this. And it hurts you inside the region. So it guarantees then for all x, when g of x is less than 0, I know that p of x is greater than 0. In this case, if I wanted to, this will allow me to, for instance, prove that x squared is less than 0 in this interval, even though x squared is going to go greater than 0 outside. I just have to multiply it by a big enough polynomial here to certify that. And there's a bunch of different questions you can ask. You can also say, let's say I don't know what alpha is. Find me the biggest alpha that proves, that is sort of, help me find the region of attraction. And the version I actually wrote was, I said, I want to maximize rho subject to, let me see, well, okay, this is what I want to write because it's the easiest thing, but it's not it doesn't quite work, and it's important. Why? You'd like to say that whenever v of x is less than or equal to rho, implies that v dot of x is less than 0. If I can say there's a sub-level set of v, so v is a function x squared here, okay? This is v, I'll do it here, v of x. This is rho, okay? The place where v of x is less than rho defines some region. I'd like to say inside that region, v dot is going down. V dot is less than 0. So I can do that with my Lagrange multiplier trick, saying whenever v of x is less than or equal to rho, certify that v dot of x is less than 0. Okay, so what would that look like? That would look like v dot of x plus lambda of x v minus rho is sums of squares. That's a constraint I can write. The problem is that lambda has some coefficients in it too. So I'm asking the optimizer to find the coefficients of my Lagrange multipliers here, and that means I can't simultaneously ask it for rho. There's a small twist on it which also certifies this, which is asking the opposite way. It says, if I can guarantee that if v dot of x is greater than 0, that implies that v of x is greater than rho. That's another way to ask it, saying if I'm able to find a place where v dot is greater than 0, then I have to be outside my region. If you work through the logic, that's equivalent. And I can write that constraint down in a nicer way. Now I get v of x minus rho minus lambda v dot of x is sums of squares. So you can ask, what's the biggest rho, maximize rho subject to this condition? And it has to find a bunch of things. It has to find rho, it has to find the coefficients of this Lagrange multiplier matrix, and it actually even has to find the Q matrix that's hiding in the sums of squares proof. But as long as they all come in linearly, that's all good. SDP can handle that. Okay? And it does. Okay, so v is just x squared. V dot is partial v partial x times my dynamics. Okay, I'm going to make a new sums of squares polynomial. I'm saying set up some variables, make my q's, whatever, so that lambda is a sums of squares polynomial in the variables x up to degree 4. And then I'm going to add an additional sums of squares constraint saying v minus rho. I have to knock out the origin, like we did before. I want to allow that it's also, I multiply by x squared just to knock out the origin. Minus lambda times v dot. And then maximize rho. Okay? And that'll solve, and it says, I've verified that that v squared, v equals x squared, anywhere that it's less than 1, basically, is inside the region of attraction of the origin. Okay, so this gets really powerful really fast. So you can do your uncertainty. Let me So what if I have uncertainty? I can, if I take that same thing and I start adding uncertainty like this multiplicative uncertainty, then what's that going to do? That's going to just change the shape of my curve. Okay? I can find a V. I don't know why it's rendering so badly. But okay, I can find a V. That same V will help me certify the region of attraction, which for the uncertain system now is only sort of the worst case region of attraction over that domain. It gets interesting if you start adding additive uncertainty, because what happens to the function then? It moves up and down, right? So where's the fixed point, right? We don't know where the fixed point is. So if you ask me for V to be strictly negative over the interval, it's going to say, sorry, I can't prove stability to the origin. But you can ask questions like, if I stay inside that region, if I start inside that region, will I stay inside that region? Okay, this is a cool example. This is the van der Pol oscillator, the curve that you get from a van der Pol oscillator, which is just a second order polynomial system. And so the van der Pol oscillator is an oscillator, right? It goes, if you simulate it forward, it'll start going around that outer curve. If you reverse time, if you just run it backwards, then everything that's inside the circle goes to the origin, and everything that's outside the circle blows up to infinity. The same way it converges to the limit cycle in forward in time, if you reverse time, it goes away from the limit cycle. So it's a cool example where the region of attraction is known. You have to simulate it numerically. But it's a funky shaped region of attraction to the origin, but it's a polynomial system, and I know what the region of attraction should be. I ask for a sums of squares, the Lyapunov function that certifies that, and it's conservative, but it comes up with this gray region, which is the inner approximation of that. That's a degree 4 polynomial. It's not an ellipse. You can have higher degree polynomials. Okay? But it also works for all kinds of systems. So for instance, the energy shaping controller we swung up and then we switched to LQR at the top. It's kind of annoying to have an arbitrary decision of when do you switch. Now you can ask the question really nicely. You could say, I've got a linear controller at the top. Can I find the region of attraction for that linear controller and then switch once I enter the region of attraction? You can do that for pendulum. You can do that for quad rotors. That's probably asking me for permission to play the video. And you can come up, like in a heartbeat, you come up with the region of attraction, an inner approximation of the region of attraction for the quad rotor, the linear controller on the nonlinear system. And you'll do that in the problem set for one of them. Okay? The other thing that I want to just drive home is that we're talking about convex optimization. That doesn't mean the region has to be convex. The convexity of the shape is different than the convexity in the parameters. So here, to drive that home, we found some weird polynomial system where the region of attraction was known and was very non-convex. And the thing you fit inside that, if you fit an ellipse inside it, you get the gray region. If you fit a higher degree polynomial, it finds the inner approximation, which is that yellow. Okay? And actually, the weird thing is, it's hard to measure volume of a high degree polynomial, so the way you grow the yellow is by pushing out on it with the ellipse. Okay, I'm out of time, but this is a really big thing that took us from sample points to for all x. I believe it's the only way to scale the high dimensions, really scale, and have certification. There are other algorithms that do for all x, but I think for all x is critical.